In the cover image, you can see a beautiful example of joint sets. When there are a number of parallel joints formed in an outgroup in a region, we call it joint sets because they make a set. If it's only one or few, then we just say joints. So in this picture, we have a beautiful joint set, perfectly parallel aligned in one direction. And you can see during the formation of joint, um, some gap open up inside the rock, and that gap is filled by a secondary mineral. In some cases, it's calcite, quartz. It can be different type of mineral, whichever um, elements are a bit present in the fluids, kind of perforating around. Those elements will form different types of minerals in the gaps. Sometimes they are not filled. We can find just gaps as joints without any filling. But in most cases, they will be filled because during extensional deformation, lots of fluids involved in the deformation, especially if it's a low angle fault controlling extensional deformation. So because of that, here on the outcrop, you can see this dark colored rock, which is the host rock. It's after brittle deformation under principal stresses in the region. This host rock is now fractured. Lots of joints form in the same direction. That indicates basically just by looking at this photo, you can make lots of interpretation already. Without even measuring anything in the field. So just by looking at this photo, what I can say, if I know directions, if this way, if these structures, for example, oriented parallel to north-south direction, I can say all the joints form in north-south trend. And as a result of that, I can say opening direction is east-west. So this opening direction you will see in a couple slides. This opening direction of joints gives you direction of sigma 3. So in this region, I can say for this example, sigma 3 is east-west and sigma 1 will be perpendicular to these fractures. And because I can see only one direction, I don't see multiple directions. Maybe one over here. There's one other direction here and maybe a little one here. So, but overall, this outcrop displays same structural pattern with same or similar orientation, which means there was at least one brittle deformation stage. If you see, other than this, if you see these type of structures not in north-south direction but at northwest direction, making another set, you can say there is a second brittle deformation stage. So you investigate what changes stress distribution in this region from north-south to northwest-southeast joint fracture formation. So that's a good research question for this type of regions. In most cases, this type of outcrops are very good indicator of extensional deformation in the region. And as a result of that, for example, these type of gaps or joints will increase the volume of the rock. Just imagine this before these joints, this rock was just one solid rock body. And after brittle deformation, these small pockets and gaps opens up inside the rock like a torn plastic wrap or paper. And as a result of that, you increase porosity. So it can be a good news, right, for natural resources exploration, because we want to know, for example, if there is hydrothermal fluids rich in gold, as an example, or silver, we want to know what's the porosity of the rock. We want to know if there is, other than primary porosity, which is a result of sedimentary processes, is there a secondary porosity, which is a tectonic or mechanical porosity? As a result of deformation, rocks can increase porosity by as a result of formation of this type of joints. And these joints will be filled by those hydrothermal fluids carrying lots of economically valuable elements and minerals. In this case, for some regions, for example, some parts of Nevada, this is an example. So you will find these joints and fractures all mineralized. So when you find general trend of these fractures and joints, basically you find general gold trends or silver trends. That's an example to applications. So I will give more examples for applications of these subjects, but definitely brittle deformation is one of the most important subjects in exploration and industry. So brittle deformation, it's break and cohesion of rock. So along the break, as we said, chemical bonds will be broken. So mineral fragments or fossil fragments, whatever is making up the rock, it will be broken. And along the broken surface, because bonds are disconnected, like this spring net. In the first example, we have spring net connected, and if you pull one of these pink or purple ball in one direction, all of the springs will move with that motion. And if you extend springs in one direction, you can do that not infinitely. There is a limit because of the strength of each spring. So once you exceed that, strength of each spring, one of them or maybe all of them will be broken at some point. So because of the stored strain energy inside the, material. As a result of that, this material will be broken, and that break is basically disconnection and transfer of strain energy from point A to point B. So because of this broken plane or broken fracture plane or surface, now it's like disconnecting highway. So you cannot transfer these cars from point A to point B anymore. They can be transferred only here within the segment. As a result of that, because of the disconnection and break, rock will lose cohesion. So rock will be weaker, like a broken bone. So once you break your leg, that's your weak point, right? So this is the result. It results in the release of elastic strain energy. So before this point, at this stage in the middle diagram, these springs store lots of energy because you are pulling springs in one direction, and as a result of this tension, lots of strain energy will be, elastic strain energy will be stored inside the material. In this case, just imagine, in micro scale, think about those molecules and elements making up this material. So you are pulling everything in atomic scale. And these chemical bonds are being kind of challenged with the stretching. And at some point, chemical bonds cannot take it anymore. So you are going over that internal energy, and chemical bonds will be broken. At this point, the expression of this atomic scale deformation from outside will be a broken surface or broken plate. So in this case, rock is weaker, and this is non-recoverable, irreversible, permanent change. That's why we call it brittle deformation. So brittle deformation can produce different types of products. One of them is joint, or you can hear tensile crack. These two terms are replaceable. And shear fractures or shear ruptures, and frictional sliding and cataclastic flow. These four different types of structures are typical characteristic features of brittle deformation. And fault planes, faults also included in this category. So faults are one type of shear fracture. Because of shear stress acting on the fault plane, we can measure some slip. So that's a different type of shear fracture. In larger scale, instead of saying shear fracture, we call them faults. And in this slide, you can see some figures explain how they form under specific stress distribution and what's the orientation of each structure with respect to stress, principal stresses. So you really have to know what's the stress orientation during joint formation, in which direction sigma 1 and sigma 3 will be oriented with respect to the orientation of joint inside the material. And also for shear fractures, If it's a Coulomb shear fracture, you need to know what will be stress distribution around that stress fracture or shear fracture. In that way, you can use fractures as a really good key structure in the field to estimate principal stress distribution in the region. Because like I explained in the first cover image, if in a region, let's say you are assigned with a project and your field area, you can see some fractures oriented in north-south direction, and in the same area, you also discover some other fracture sets in east-west direction. Because if you know in which orientation sigma 1 and sigma 3 act on these planes, you can basically understand that these two fractures cannot form at the same time under exactly same stress distribution, which means this region experienced some change in stress field. So distribution of principal stresses must have changed over the time from east-west to northeast or north-south to east-west. So what I mean here in this figure, for example, we have an undeformed sample, and this undeformed sample is now under vertical sigma 1. This is the axial loading direction. And then we have sigma 3 sideways. That's the minimum principal stress. Sigma 1 is always greatest. Sigma 1 will be always biggest number, and sigma 3 will be least or minimum principal stress in regional scale or other scale. So in this case, these are all compressive stresses. We just compress this material more in sigma 1 direction. It's because it's maximum principal stress. And in east-west direction, we apply less and minimum compression. So under this kind of stress distribution, rock mechanic experiments show that joints will form perpendicular to orientation of sigma 3. So you should note that joints or tensile cracks will open up in the direction of sigma 3 or minimum principal stress. So whichever direction you have minimum principal stress in the region, then these joints and tensile cracks will open up in that direction, like this kind of narrow eye shape or almond shape. And this gap can be filled by a secondary mineral like calcite or silica mineral, or a different type of some material can be injected. It can be fine-grained sediment as well. And this is how during joint formation, principal stresses will be oriented relative to orientation of joint. So if this is the map view, by the way, and if you measure orientation of this joint, sigma 1 will be parallel to the strike of the joint in the field, and sigma 3 will be perpendicular to strike, and it will be parallel to opposing direction. And this is an example of shear fracture. Because of the shear stress acting along the plane, there will be some sliding and some offset. So faults are one type of shear fracture, basically. And difference between joints and shear fractures, if you can compare these two, joints will not produce any displacement or offset. It's not like a fault plane. So in the field, on an outcrop, if you find a fracture plane, a broken plate surface, and you can't make sure is it a fault or not, first thing to check is there any displacement? Is there any evidence for slip on one side of the fracture plane? If you can find any evidence for displacement, slip on one side of the fracture plane, then it can be possibly, most likely, it is a fault plane. If you don't see any evidence for slip or offset, if marker layers are not displaced, then it is possible that you are measuring a joint or tensile crack. And sometimes the secondary filling is also helpful, because in most examples, we see joints and tensile cracks filled by a fine-grained sediment or some kind of secondary element, secondary mineral. In frictional sliding on a reactivated joint, sometimes after this joint forms under this stress distribution with vertical sigma 1 and horizontal sigma 3, stress conditions can change and direction of principal stresses can change. As a result of that, if we change direction of sigma 1 and sigma 3 with respect to this already formed joint, then type of motion will change. It's like when two cars hit head to head, that's one type of crashing and deformation. And you can basically imagine kind of it will form an accordion shape and that will be folding. And if a car hits the second car at an oblique angle, it's a different type of crashing and deformation. And that angle between the direction of the motion will create different type of structures like this. So if you put sigma 1 and sigma 3 in this figure, for example, for this case, sigma 1 orientation will be here in this direction, like this, oblique, and sigma 3 will be somewhere here. So it is not this distribution anymore. So with a slight angular change in the distribution of sigma 1 and sigma 3 can trigger this type of strike slip motion. So this motion occurs parallel to the strike of this plane. There is a vertical plane. This is map view again. So if this is mapped view, and if you look down here along this line, there will be a vertical plane. So all the motion and sliding occurs along this vertical plane. And that's the fault plane in this case. And during cataclastic sliding on a former joint, basically cataclastic sliding will be similar to this frictional sliding, but difference is pressure will be really high, and as a result of that increased pressure, along the broken surface, rock blocks will grind each other, and as a result of this kind of milling and grinding motion, rock fragments will be rock grain size will be reduced, first of all, and also broken rock fragments will form this cataclastic zone in between two moving fault blocks or fracture blocks. And here also, if it's a shear zone, then you will see some kinematic indicators for shear deformation. And without losing cohesion, rocks will be just stretched and elongated. So there will be a shear zone between two moving fracture planes. So these are different types of products. And if we just go into details a little bit more, we can basically categorize these fractures as mode 1, mode 2, and mode 3 displacement features. So mode 1 displacement, in this kind of deformation, brittle deformation, tensile cracks open in the direction perpendicular to the crack surface. They will form basically perpendicular to sigma 3 direction. So here, this is the direction of sigma 3, and they will form, open up. The opening direction will be sigma 3, but the propagation of joint in this direction or strike of the joint will be perpendicular to sigma 3. And mode 2 displacement, it's sliding mode. Rock on one side of the crack surfaces moves very slightly in the direction parallel to the fracture surface. In this case, some offset will displacement will form during the deformation. As this fracture propagates in one direction, displacement can increase with increasing length of the joint in one direction. And mode 3, it's a different type of motion. Instead of this sliding along the strike, material can be basically deforming in tearing action. So in tearing mode, rock on one side of the crack slides very slightly parallel to the crack, but in a direction parallel to the fracture front. So it is like exactly tearing the paper. So one side of the block can be dropping down and at the same time sliding. It's kind of like it can be an oblique motion. And this can be observed at many different scales. You can see this type of tear faults in regional scale, global scale, or they can be just microstructures or outcrop scale structures. So in mode 1 type of displacement or deformation, tensile crack or mode 1 fractures will form. So you can see these terms replace each other, like mode 1 fractures, tensile cracks. These are all same things basically. So under vertical loading, sigma 1, maximum compressible stress in this direction, these tensile cracks will again open up. This is a really good analogy. Here we have an envelope with one side open, and if you push this envelope from top, from edge, this open end will open up in this direction, which is perpendicular to compression direction. So this is basically what we observe in the field as joint or tensile crack. So sigma 1 in this case will be parallel to the strike. This is the strike of the joint, and it is vertical structure. So in most cases it will be vertical, so you don't have to dip direction. Dip angle will be 90 degrees or sub-vertical. And an opening direction here will give you estimation of sigma 3 orientation. So why why this is important? Because first of all, the first thing when you deal with deformation for any type of project, it can be industry or academia. So when you deal with deformation in the field or on a hand specimen, the first question you have to ask yourself, what type of structures formed and what is the stress distribution? If you know stress distribution, first of all, you will understand if there's only one deformation stage or if it's a multi-deformational stage affecting region. And secondly, you will be able to figure out what other type of structures are most likely to form in this region under same stress distribution. Because when we say structures, it is not only faults or it is not only joints. There are hundreds, thousands of different types of structures formed during deformation. It can be a stylolite, it can be fold, it can be cleavage or foliation, or mineral stretching lineations. There are so many different structures. In larger scale, it can be different types of faults, strike slip, normal, reverse faults, or oblique faults. So what type of structure will form exactly when, under what stress distribution? You need to know this. If you know this stress and structure relationship in the field, it will be easier to make some analysis with just some simple field measurements. So during in this experiment, we have axial stretching under low confining pressure. And in the second experiment, we have axial compression under low confining pressure. And these vertical cracks are basically tensile fractures formed during this axial loading. And this is an example to joints you observe in real life in nature. And here we have an example also, an image from these experiments with increasing strain, increasing stress, and you can see with increasing strain, material will first form this kind of very fine barrel shape, and it will form a perfect barrel shape here with some fractures, some Griffith cracks. And at the end of this experiment, material is shortened. So you have to notice that material length is different. So between this late stage of the formation experiment and early stage, which is undeformed state, you should be able to make a calculation for example, elongation, E. So if you measure this length after and before the formation, you can find E elongation number, because after deformation length will be shorter, so E elongation number will be negative number, which refers to compression and shortening. With comparing this kind of length changes, you can also estimate what type of deformation was happening in the region. Is it extensional or compressional? Here we have some examples of joints from field. On this field photo, you can see it's perfectly parallel linear alignment of joints, as if someone came and cut this outcrop with a knife. So you can see these joints in one direction are perfectly parallel in this direction, and there is another set here in this direction. Those are also perfectly parallel joints in another direction, and these perfectly perpendicular two joint sets form a cubic blocks inside the outcrop, and this is one type of joint distribution you can see in the field. And when you find something like this on the outcrop, first you have to measure strike and dip base. But first of all, fractures are planes, so we measure strike and dip direction. So when you find an outcrop like this, first thing to measure is the strike and dip angle of each fractures on the outcrop. And you need to make a note for each set. So this is one set in this direction. You can say maybe joint set 1 or joint set A, and then you can measure joint set 2 or joint set B. And after you collect these measurements, you will use these measurements for structural analysis, and you will plot them on a stair net, and you will show how their dip angle, how their strike orientation changes. And this is another example. Sometimes joint surfaces can be very confusing in the field, because they will be just a smooth plane looking like a bedding plane or fault plane. So first you have to find out, when you find a surface like this in the outcrop in the region, before jumping on a conclusion and saying, oh, there's a fault plane. First you have to study this outcrop and make sure if it's really a fault plane or joint. So again, how do you distinguish joints versus faults? Joints will not produce displacement offset. Fault planes will produce offset or displacement and slip. So here in this outcrop, first you find bedding planes. For example, here we have these bedding planes oriented in this direction, very steeply dipping bedding planes. So when you have an outcrop like this, another thing to measure is bedding, strike, and dip. And then you study this surface. Is it changing orientation of bedding planes on the other side? Is it producing some kind of slip and offset? If not, then you can basically measure strike and dip of the surface and make a note and say it is joint cutting through bedding planes. After you find one or two joints in an outcrop, the second task should be finding same or similarly oriented structures on the outcrop. You have to make sure if it's a regional scale joint formation. In this case, if it's a regional scale deformation or the deformation stage that affecting your whole study area, you should be able to find more than one or two joints in the same outcrop oriented similarly. If it's only one or two, it can be related to, for example, blasting. Blasting will produce lots of fractures, not tectonic fractures, but human-induced structures. So you should be able to distinguish, those structures from tectonic structures, because those human-induced fractures will not demineralize, right? They will be, so you can't just blast an outcrop and inject gold, but those tectonic fractures will be what you should be looking for on the outcrop. So that's why when you find a joint surface like this, always look for others on the outcrop in the same orientation. If you find joints oriented in multiple directions. It can be a result of multi-stage deformation. In this case, you have to look for other evidence to understand changes in stress field. Like this outcrop, for example, here we have similar to this one. It is like combination of these two. So we have this perfectly perpendicular two sets in one direction here, another direction here. And now we have these other fractures oriented in this direction, in this direction. So these 1, 2, 3, maybe even more. This is just a piece of outcrop. So there is at least 1, 2, 3, maybe even 4 different joint orientations on this outcrop, which means either this region experienced 4 different brittle deformation stages with 4 different principal stress distributions, or some of these structures can form synchronously if they are, if for example, if this one and this one show any shear shear stress, shear motion, shearing, then in this case, maybe some of them can be conjugate. So we have more examples here. These are bedding planes, and you can see at the surface of this outcrop, these lines perfectly aligned parallel, those are fracture planes. So we are looking down on vertical joints at Arches National Park, Utah. And gapping joint set is aligned southeast, northwest in this case. Joints can form depending on the rigidity of the beddings or layers. These joints can form as a continuous structure, or they will be just confined within one single layer. So here on this slide, you can see this light color, white color refers to soft, and darker colors refer to stiff rock layers. And here we have these layers with different rigidity. So some layers are soft and some layers are really hard and stiff. So in this case, the stiff layers will be broken because they will be fragile. They will be like glass. And the softer layers can accommodate, basically they can store more strain energy. And because of that, under same stress distribution, while this layer is broken and fractured, like a glass, this softer layer will still, store lots of strain energy because that applied stress is not enough to fail it. So in this case, joints will be confined within the stiff layers, and it will not show any evidence for brittle deformation in soft or relatively softer layers. If it's, and with increasing rigidity, basically you can see these joints can propagate and they can get connected. We call it linkage, joint linkage. As a result of joint linkage, these joints can grow out in one direction and they can become continuous structures. And other new structures can form at the same time. So bed-contained and through-going joints can form on the same outcrop like this example. So these are what we call bed-contained because they are just contained by one single bedding plane. And these are continuous or through-going joints, and they can be present together on the same outcrop. Shear fracture. A shear fracture is basically defined by a surface across which a rock loses its cohesion when shear stress parallel to the surface is sufficiently large. So in this case, some higher amount of shear stress involved in the deformation. So along the fracture plane, there's more an increased shear stress acting parallel to surface, and that's basically this is the force, this is the stress, trigger motion, trigger sliding along the plane. Under relatively lower shear stress conditions along the plane, there will be no sliding or slip. It will be joint formation. And after increasing shear stress parallel to surface of the joint, that shear stress will basically control sliding, and these shear fractures will form inside the rock. So why these shear fractures are important? Using these Mohr circles, we can analyze them, and also with using them, we can estimate the tensile strength of the material. We can estimate direction of principal stresses and the formation stages. So these transitional tensile fractures, for example, these fractures, when you plot them on a Mohr circle, the Mohr circle will be tangent to the envelope at 2 points rather than 1 at the time of fracture. And these fractures are roughly 30 degrees to sigma 1 orientation, which means when you find transitional tensile fractures in the field, so you can estimate direction of sigma 1, which will be 30 degrees to the fracture orientation. And also another thing, sigma 1 is nearly equal to 3 times of tensile strength of the rock in order to form this type of transitional tensile fracture. So just by, if you determine and identify type of fracture, is a tensile fracture, is a transitional tensile fracture, do you see some initial, sliding or not, then you can talk about tensile strength of the rock already. And this transitional tensile behavior can be described by a graphic law of failure, if you know from rock mechanics. And this is the equation. Basically, critical shear stress required for failure, which is this one, depends on the tensile strength of the rock, which is T0 over here, and normal stress acting on the fracture. So what's the amount of normal stress and what's the tensile strength of the rock? These two parameters will control how much critical shear stress required for failure. And there is an example question. So in the project area, if you know tensile strength, if you know minimum, maximum principal stresses, and you can calculate critical shear stress required for forming fractures at this desired dip angles. So for this type of question, first of all, in the equation we have normal stress, but in the question you have principal stresses, which is sigma 1 and sigma 3. So first you have to calculate normal stress from this, with these two numbers. So 60 goes to here and 20 goes to here. With dip angle of fracture, we have two scenarios. One is 45, another one 60. So first you need to solve this question for 45-degree dip angle, which is angle theta over here. And then first you find normal stress for 45-degree dip angle. And then use this number here in this equation. And because you already have tensile strength of the material as 40 megapascal, you know this number. So you find critical shear stress required for failure in order to form a fracture with 45-degree dip angle. Then you solve same question for 60-degree dip angle. In this case, angle theta will be 60 over here, and you will use same parameters for the rest of the equation. Please try to solve this equation and this example. The more examples you solve, the better you will be prepared for exams and also future structural analysis. Coulomb fractures, in this type of fractures, they form, the sigma 1 has to be at least 5 times greater than tensile strength of the material. So shear stress should be really, really increased along the fracture. And rock strength increases linearly with increasing confining pressure. And this is the equation for critical shear stress calculation. Again, it depends on normal stress in angle of internal friction, different than previous equation. And we use also coefficient of internal friction. Joints and veins. Veins are also fractures, natural fractures, but veins are filled with minerals or igneous material. If basically veins and joints, they form together, hand by hand, when joints form and gets filled by a secondary mineral, that filling inside the joint will be a vein, basically. That's the relationship between joint and vein. So joints are the gaps, that's the cast, and vein is what's filling inside the gap. And orientation of veins, also another thing to measure in the field. If you have lots of veins in parallel alignment, that's another type of measurement you should collect and investigate, because like I said, veins will form as natural fractures filled by secondary minerals. So joints are tensile fractures that form perpendicular to the minimum principal stress. Never forget this relationship. Always remember how sigma 1 and sigma 3 will be oriented around a joint or shear fracture or Coulomb fracture. So when you have conjugate fractures like this, so conjugate means basically two fractures will be oppositely dipping like this. And in most cases, that will be a 60-degree angle between two plates. So in this case, bisector of the 60-degree angle between two fractures. Let me show it here. Let's new share, whiteboard, share. Okay. So when we have one joint, one fracture, shear fracture in this direction, another shear fracture in this direction. So these two fractures are called conjugate shear fractures. So these conjugate shear fractures are really good tools, structures to estimate direction of sigma 1, because sigma 1 will be bisector of this narrow angle. And that will be, in most cases, that will be a 30-degree angle between sigma 1 and fracture plane. So if you find this type of conjugate shear fractures in the outcrop, you can use them as a good tool to understand direction of sigma 1, maximum principal stress. So importance of joints, they provide history of stress and strain in the region. They control landscape morphology. And also they affect rock strength and permeability and porosity. They create a secondary porosity, which is basically, that's how they produce unconventional petroleum, right? They are fracking rock, forming fractures, forming tensile fractures, and as a result of those tensile fractures, increasing porosity and connecting disconnected pores and increasing permeability. That's how we produce unconventional petroleum in the North Dakota, right? In North Dakota. And other than this, also, other thing is when we inject fluids in order to form joints and tensile cracks inside the petroleum-bearing rocks. what other things happening is we are changing deviatoric stress. Remember from example question from in the lab, the very last question in more circle, more diagram lab, we changed not the size but location of the more circle with injecting some fluids, and we basically pushed circle to the left and made it touch Coulomb failure envelope, and we failed the rock. That's the moment basically you form a new fracture inside the rock. So at this time, because we change fluid content and forming new fractures, with changing stress and shear stress conditions inside the rock, some previously formed or existing fractures can also slide and produce slip. That's basically a really interesting phenomenon that people still investigate. You remember if you read news about earthquakes in during hydrofracking. So that's an interesting subject. We can talk about this later, especially during Falls lecture. But definitely, these human-induced, jointing or fracturing rocks have some relationship with producing earthquakes simply by changing the composition and stress distribution around the rocks. So that's why we need to understand how rocks behave during brittle deformation and in what orientation joints will form with respect to stress distribution in the region. So here, last example, this is a bedding plane, and these vertical cracks you can see on the outcrop, even here, they are parallel aligned joints going through bedding planes. So for this type of outcrop, we have to measure strike and dip of bedding plane and then record also strike and dip of each joint plane for structural analysis.